Hello. In last lecture, we have just started our new chapter, which is transmission line, and we have already discussed about what is transmission line and which are the transmission line parameter, and we have to just start our second question, which is derive the equation of voltage and current on the transmission line. And we have already discussed about what do you mean by the unbounded medium and bounded medium. There are the two types of the bounded medium, transmission line and the waveguide, and we have to discuss here the transmission line. These are the example of the transmission line. Okay, and we also discuss, that means we have also discussed about how the transmission line, okay, how it works. Okay, so we have to just take the example of the coaxial cable line, and this one is the parameter of the transmission line. Which are the parameter of the transmission line? Resistance, inductor, conductance, and the capacitance are the parameter of the transmission line. Okay, and in last lecture we draw this figure. Okay, so now we start to write a Kirchhoff current law, okay, or Kirchhoff voltage law. So initially I have to write a Kirchhoff voltage law for this loop. So apply Kirchhoff voltage law, KVL. Okay, so if you apply the KVL, so you can write V of ZT is equals to, here the resistance is present, which is R delta Z, and which current is flow through the resistor, which is I of ZT, plus inductor is present, and we know that the voltage across inductor is L di by dt. Okay, see here, first of all I have to write here voltage across resistor V is equals to IR, voltage across inductor V is equals to L di by dt, and current through, okay, so voltage across inductor, and current through capacitor I is equals to C dV by dt. Okay, we need these three equations. So R delta Z, I Z of t. Then what about the inductor? Voltage across inductor is L delta Z, L di by dt, so this di of Zt by dt. Okay, then these two components which are connected in parallel. Okay, so this conductance and capacitor, these both are connected in parallel. So what is the voltage across these two components? It is nothing but V of Z plus delta Z into T. So to directly write here, it is plus V of Z plus delta Z into T. Okay, now to rearrange this term, so you can write in this way, V of ZT, I will take here in this side, in the left hand side, so it is V of Z plus delta Z into T divided by delta Z is common, so I will take at the denominator side, is equals to R I of ZT plus L di of ZT by dt. Okay, so this one is nothing but just the voltage difference at the source side and at the load side with respect to delta Z. Okay, so it is nothing but dV of ZT divided by dZ is equals to Ri of ZT plus L di of ZT by dt. Okay, so now you can, okay, here inductor and resistors are present. Okay, so you can draw all, okay, or you can write this equation in a Phasor form. So how can you write this equation in a Phasor form? So if you write this equation in a Phasor form, so it is nothing but you can write in this way. So if you write in the Phasor form, so no need to write Z and T, you have to just write this dV of dZ. You can write here as the source side. Okay, S is indicate source side, source voltage, is equals to RIS source current plus now I have to consider, if you write the equation in terms of Phasor form, so you have to consider the capacitive reactance, which is XL. This is known as capacitive reactance, XL into IS, because you have to write in the Phasor form. Okay, so it is I have to again write this equation. So this dvs by dz is equals to ris plus xl is. What is xl? J omega l. Okay, so it is r plus j omega l into is. Okay, so we will get this equation dvs by dz is equals to r plus j omega l into is. If I have to apply a Kirchhoff voltage law, KVL. Okay, now I have to apply a KCL at this node, Kirchhoff current law at this particular node. This one is a node. Okay, so now I have to apply a Kirchhoff current law, KCL at this node. Okay, so this one is my incoming current and these two are outgoing current. So you can write I of zt is equals to delta I plus I of z plus delta z into t. And what is delta I? Delta is delta I1 plus delta I2. Okay, so apply KCL at this node. So you can write in this way. Now apply Kirchhoff current law at this node, at the given node. So this I of zt is equals to delta I, this delta I plus I of z plus delta z into t. Okay, see here, don't be confused about why I have to write z of t. Okay, is here this z of t is already present here, v of zt, because here the voltage whatever the voltage or whatever the current is present is a function of this distance. Okay, see here, actually in this case at this particular starting point the voltage is maximum, which is Vg, and if you go throughout your two parallel wire transmission line, so at this point the voltage is lesser than the Vg. Okay, that means the voltage is dropped or the voltage is dissipated. Okay, so the voltage is dropped due to this distributed parameter. Okay, so we can say that the voltage is a function of the distance, or you can say that the voltage is a function of the length of transmission line, and it is also a function of time. So that is why I have to write v of zt. Okay, so don't be confused about it. Why I have to write v of zt always and always. Okay, so this I of zt is equals to delta I plus I z plus delta z into t. What is delta I? Delta I is delta I1 plus delta I2. So delta I is delta I1 plus delta I2 plus this quantity. Okay, so I have to take this quantity here at the left hand side. So this I of zt minus I of z plus delta zt is equals to delta I1 plus delta I2. What is delta I1? Delta I1 is nothing but the current which is flow through the conductance. And what is delta I2? The current which is flow through the capacitance. So across conductance and capacitance, what is the voltage? The voltage is V of z plus delta z t. Because these two components are connected in parallel, so voltage are same, which is V of z plus delta z into t. So across the conductance, the voltage is this one, and across the capacitance, the voltage is same, this one. Okay, so what is delta I1? Delta I1 is G delta z V of z plus delta z t. Okay, and what is delta I2? Delta I2 means the current which is flow through the capacitor. So we have to use this equation, C dV by dt. So this C delta z dV by dt, but which voltage? V of z plus delta z comma t. Okay, so delta z and delta z I will take at the denominator side. Okay, so I will take this delta z at the denominator side. Okay, so again it is I of zt minus I of z plus delta z. So it's just a differentiation. Okay, so you can write in this way, di of zt by delta Z is equals to G V of Z plus delta Z into T plus C d by dt V of Z plus delta ZT. Okay, now we have come at this point, we have to apply the Phasor representation of this equation. We have to apply the similar here, the Phasor representation of this equation. So the Phasor representation of the equation is dis by dz is equals to G voltage Vs voltage. It is, see, actually it is V of Z plus delta Z into T. So you cannot write here it is Vs, because what is Vs, actually we have to consider is a source voltage and this one is a load voltage, but delta Z is the size of this transmission line and delta Z is very small compared to the Z. Okay, so if I have to add Z plus delta Z, you can neglect the delta Z in that case, because delta Z is very small. So this V of ZT, it is nothing but Vs plus C, and okay, I have to again apply the concept, the same concept that we have already applied in the case of inductor. Okay, in the case of capacitor you can apply the same concept. Okay, so this is nothing but Vs into, okay, Vs into Xc, and what is Xc? Xc is 1 upon j omega c. Okay, Xc is nothing but, okay, so here it is Vs by Xc. So this equation is dis by dz is equals to Vs is common, G plus 1 by Xc. Xc means 1 upon j omega c. Okay, so Xc is 1 upon j omega c, denominator, okay, so this G plus j omega c. Okay, so we'll look at the second equation. Clear? So now finally I have two equations, first equation and second equation. Okay, now what I have to do, I have to do the differentiation of my first equation with respect to Z. If I do the differentiation of my first equation with respect to Z, so this square Vs by dz square is equals to R plus j omega L dis by dz. I have to put the value of dis by dz from the second equation. Okay, so do the derivative of the first equation. So if you do the derivative of the first equation, so this square Vs by dz square is equals to R plus j omega L and dis by dz, which is G plus j omega c into Vs. Okay, now we assume this term is nothing but my gamma square. See, we have to do the same calculation in deriving the wave equation. Okay, we do the similar calculation here. So this square Vs by dz square minus gamma square Vs is equals to 0. Okay, so it has a two solution. How can you find out the solution for this case? Okay, it's a second order linear differential equation. Okay, so this m square minus gamma square is equals to 0. So m is equals to plus and minus gamma. So it's a two solution. Okay, so Vs of Z, because I will take the differentiation with respect to Z, is equals to, is a two solution, is a constant e raised to minus gamma Z plus p times e raised to plus gamma Z, because it has a two solution plus and minus. Okay, so which solution is valid, e raised to minus gamma Z or e raised to plus gamma Z? Now the main thing is, what is Z? So Z is nothing but this distance is known as Z. Okay, Z is nothing but this distance from Z to Z plus delta Z, it's a Z. Okay, so which solution is valid for this case? So we can say that both the solutions are valid. Okay, now the question is how both the solutions are valid. So see here, if you go from source to the load, if you go from source to the load, so at the source side the voltage, suppose for okay, take the example, at the source side the value of voltage is 100, at the load side the value of voltage is 90. Okay, that means the 10 volt is dropped between source and load. Clear? So at the source side the voltage is 100, at the load side the voltage is 90. Okay, so it's a positively voltage. Okay, the positively voltage is propagated. If you go from load to the source side, so at the load side the voltage is 90, at the source side the voltage is 100, so it's a negatively voltage propagation. Okay, so see here, the first term e raised to minus gamma z, okay, it's a negative sign. Negative sign means the graph is exponentially decreasing. This negative sign is indicate that this, okay, exponentially the graph is decreasing. Decreasing means here it is 100 and then it becomes 90. Okay, so this term is from source to the load, that means positively voltage propagate. What about this term is a exponentially increasing, that means from load to the source, from 90 to 100, so it's a negatively voltage increase. Okay, means negatively voltage propagate. Clear? So both the terms are valid term. Okay, so you can write in this way, what is A0? A0 is the maximum value of voltage which is V0, e raised to minus gamma z. Okay, we will discuss about what is gamma. Okay, B0 is also V0 e raised to minus, sorry, e raised to plus gamma z, but in this case we have to consider it is 100 and here we have to consider it is 90. Okay, so how can you separate this to V0? So this V0 plus and this one is V0 minus. Okay, so what this V0 plus say that, what do you mean by the V0 plus quantity? Okay, V0 plus is indicate that it is from this side, from positive z axis. Okay, and what this V0 minus is indicate? It indicate it's from negative z side. Okay, see here, this side is positive side. If you go from this direction, so it's a positive direction. If you go from this side, so it's a negative z direction. Okay, so you can write in this way. Clear? I think it's easy to understand for you. So this Vs of z. Similarly, we can derive the equation of Is of z. What is Is of z? Is of z is I0 plus e raised to minus gamma z plus I0 minus e raised to plus gamma z. Okay, so here is a voltage and current equation, but it's a function of z only. It's a function of z only. But if you write in a function of time also, so how can you write this equation in a time? So you can write this equation in this way: Vs, which is a function of z, and time is nothing but it is V0 plus e raised to minus gamma z, V0 minus e raised to plus gamma z. Okay, that means it is Vs of z into e raised to minus j omega t. Okay, e raised to minus j omega t, because it's an exponential term. Okay, now here what is, okay, here what is gamma? Gamma is known as propagation constant, which is nothing but the addition of real part plus imaginary part, alpha plus j beta. What is alpha? Alpha is known as attenuation constant and beta is known as phase constant, that we have already discussed in our last chapter. What is attenuation? What do you mean by the attenuation? What do you mean by the phase constant? Okay, we have already discussed in our last lecture. Clear? So alpha is the addition of alpha plus j beta. Okay, so I will just add here gamma is nothing but alpha plus j beta. This beta term is merged with this imaginary term, so you can write in this way: V0 plus e raised to gamma means alpha plus j beta, so minus alpha z e raised to it is minus j, so minus j beta, okay, e raised to minus j beta alpha into z into e raised to minus j omega t, this term, plus v0 minus e raised to plus alpha z e raised to plus j beta e raised to minus j omega t term. Okay, so I have to simplify this equation. So v of zt or vs of zt is v0 plus e raised to minus alpha z, where alpha is a attenuation constant, e raised to minus j omega t plus beta z. Okay, omega t plus beta z. Okay, here it is minus gamma and here, okay. Clear? Okay, it's fine. And what about this case? It is plus v0 minus e raised to alpha z e raised to minus j omega t minus beta z. Okay, so just is the equation of voltage and current. Similarly, you can write the same equation for current also. Okay, so here the question is, what is gamma? So here gamma is known as propagation constant. Okay, so now we have to discuss about what is gamma. So here this gamma is known as propagation constant, and we have to assume gamma square is equals to r plus j omega l g plus j omega c. So what is gamma? Gamma is under root of r plus j omega l g plus j omega c. Okay, now tell me the equation of propagation constant for electromagnetic wave that we have discussed in last lecture. Okay, in our last chapter, which is gamma is equals to under root of j omega mu sigma plus j omega epsilon. It is a electromagnetic wave propagation in which type of medium? Unbounded medium. Similarly, but for the bounded medium, which are the material property? Conductivity, permittivity and permeability. Which are the parameter of the transmission line? Resistance, inductance, conductance and capacitance. Okay, so this both is known as the propagation constant, and it is nothing but alpha plus j beta. Here it is also alpha plus j beta. The meaning of alpha and beta are same in both the equation. Alpha is known as attenuation constant and beta is known as phase constant. Okay, we have already discussed what is attenuation constant and what is phase constant. Okay, now we derive one more equation which is known as characteristic impedance. Okay, so here now equation for characteristics impedance, which is Z0. What do you mean by the characteristics impedance? Characteristics impedance means the impedance which is offered by this line. Okay, the impedance which is offered by the line, it is known as characteristics impedance. See here, if you look this line and if you measure the impedance between these two lines, okay, it is Z1. If you measure the impedance between these 2 points, it is Z2. Here it is Z3, here it is Z4, here it is Z5, here it is Z6. That means the impedance is also distributed. Okay, so this type of impedance is known as characteristics impedance. Okay, if you measure from the input side, it may be different. If you measure from the output side, it may be different. If you measure, okay, if you cut your transmission line at from some distance and if you measure from this side, so it may be different. Okay, so it is known as characteristics impedance. So characteristics impedance Z0 is equals to V0 plus upon I0 plus, we have to just apply Ohm's law, V is equals to IR. So no need to derive the equation, I have to just directly write the equation of characteristic impedance, which is nothing but R plus J omega L, this term, divided by G plus J omega C. Here it is in the multiplication form, here it is in the division form. Okay, how can you relate this characteristic impedance with electromagnetic wave propagation in unbounded medium? It is intrinsic impedance. Intrinsic impedance is under root of this term J omega mu divided by sigma plus J omega epsilon. Okay, so now I have to just compare these two. Okay, this equation is known as the propagation constant for transmission line. Here is the propagation constant for electromagnetic wave propagation. Here it is the characteristic impedance for transmission line. This one is the intrinsic impedance for wave propagation. What is the similarity? The similarity here is the first term and second term both are in the multiplication. The first term and the second term both are in the multiplication. Now here first term and second term both are in the division mode. Similarly here the first term and the second term both are in the division mode. Okay, so it is known as characteristic impedance. Okay, so Z0 is known as the characteristic impedance of transmission line. Okay, so the characteristic impedance is depend on what? It depends on resistance, conductance, transconductance, okay, and it also depends on the capacitance. Okay, so here we have to derive the equation of Z0. Okay, so if you solve this equation, so you have to find it is nothing but Z0 is equals to, it's a combination of real part and imaginary part. Okay, so Z0 is equals to R0 plus JX0. What is the unit of Z? Okay, keep in mind one more thing, unit of Z is ohm. But what is the unit of R? Ohm per meter. Unit of L, Henry per meter. Unit of G, mho per meter. Unit of C, Faraday per meter. Okay, but unit of Z0 is ohm. So that is why unit of R0 is also ohm. Unit of X0 is ohm. Okay, so this characteristic impedance has a two part. First is a real part and second is imaginary part. Okay, we have to just do the comparison like that. Okay, so now in next lecture what we have discussed. Okay, so in next lecture we have to discuss about what do you mean by lossless and distortionless transmission line. Okay, and then after we'll jump to the next topic, how to measure input impedance, what is reflection coefficient and VSWR. Okay, so we have finished these three topics. First, transmission line parameter, which is RLGC. Then second is equation of voltage and current on the transmission line, and what do you mean by the propagation constant and characteristic impedance of line. Okay, thank you.